Hi guys, so in this lecture I'll be starting on we'll be seeing some more examples of the chiral compounds, and specifically here we'll see what happens when we use nitrogen as a chiral center. Okay, so let me start off. So nitrogen as chiral center. Okay, so let's say here we have, for example, as this. Okay, so does it have a chiral center? Yes. There are four different groups attached to a nitrogen atom. It is sp3 hybridized, hence it is having chiral center and it is optically active. Okay, let us look into second example. Does it have chiral center? No. Why? It does not have chiral center because the lone pair on nitrogen are involved in having a resonance with CO group. Okay, why? Because it is sp2 hybridized nitrogen atom. Okay, let us look at third example. Here we have nitrogen, a lone pair, and three groups attached to nitrogen. So does it have a chiral center? Yes, it does have a chiral center. And is it optically active? No, it is not optically active. It is optically inactive because of amine inversion, right? So a compound undergoing amine inversion will not be counted in stereoisomers because they are conformers. Okay, so let me write the note here. The energy for the amine inversion is available at room temperature, hence the conformers are also available, in which the two formed inverted amines are in mirror images of each other, but still they are conformers, they keep on rotating, hence it is not a optically active compound. Howsoever, the nitrogen atom is a chiral center compound undergoing amine inversion. Will not be counted in stereoisomerism or in stereoisomers because they are conformers. Okay, so next question is, you have to just draw stereoisomers of the following compound and find the number of meso compound, number of diastereomic pairs, and etc. So draw stereoisomers and find number of meso and diastereomers. Okay, so let us start it. First, let's say we have this compound, and so the if you draw the stereoisomers of the following compound, then 2Cl on coming out of the plane, obviously this would be a meso compound. Okay, then we'll have something like one out of the plane, one into the plane, ClCl. Okay, and then I can have, so I hope you can see that here there are even number of carbon atoms. Okay, even number of chiral centers, and the compound is, I think, odd number, means you can also have This is a chiral center. This is a stereogenic area, and n is the number of stereogenic area, not chiral centers. Okay, so if you have across this, then this is presently, no, you cannot have across this because both the groups attached here are same, so this will not be counted as a stereogenic area. Okay, so only 4 chiral centers are there, and the compound has plane of symmetry or center of symmetry. Hence the total number of stereoisomers would be 2 to the power 3 plus 2 to the power 2 minus 1. These are the diastereomers and these are the meso compounds. So meso compounds would be 2 and diastereomers would be 3. Total stereoisomers would be 10. Okay. So one is this meso compound, and the another one can be, means I'll just come to it. So here for this you can have, let me make this as dash just for better clarity. So this is the mirror image of this, and these two are diastereomers, both coming out of the plane. Okay, so let us draw for this. Okay, this and so obviously this is also a meso compound. Why is this a meso compound? Because we have a center of symmetry here, so this is a meso compound. Okay, and we can also have this as a diastereomers. Oh, I drew this wrong. This was an enantiomer. I beg your pardon. This was an enantiomer because it was a mirror image of each other. So these two are enantiomers. Okay, so rest with this and this, with meso and enantiomer, one compound of meso and one compound of enantiomers are diastereomers. So these two, and obviously these two and this two will be diastereomers. Okay, for now I'm drawing the diastereomers. So here you can have something like this, and you can draw the mirror image of this as well. Okay, so I hope you can draw all the possible structures required for calculating the number of meso compounds and diastereomers. Okay, so for the homework problems I'll give you have to draw all the isomers possible of C5H10, not stereoisomers. Okay, include all the isomers, be it structural or be it stereo. Okay, so draw all possible isomers, structural and stereo of C5H10. Okay, so this is a homework problem. You can just pause the video, think about it, draw in your pen on a page, and then verify your results, and the answer should be okay. So this can be the first one. Second, we can start from cyclobutane ring with this. Third can be this is coming out of the plane. One can be, this is obviously a meso compound, this can be an enantiomer with this one as the pair. Okay, now ethyl group attached to cyclopropyl. Then comes we remove the ring, then just having a double bond. Okay, so for this compound, it would have two multiplied by 2 because it will have one geometrical isomer as well. Then we have this one, we can have and finally you will have. So how do I'm writing is writing, am I following a certain rule? Yes, I hope you remember RTFMCP. Okay, R stands for ring chain, T stands for tautomer, F stands for functional. So we first I drew all the ring chains. There is no tautomer involved. There is no functional group here. And then third is metamer. There is no functional group, hence there is no metamer. There is a single RT chain isomer. I have drawn for the alkene chains. And finally P is for position isomer. For the position isomer, again I have change the position of double bond in the chain isomers. So position isomer is also there. Okay, so let us draw all the possible structural isomers of this. All possible isomers of C4H8. So if you calculate the dB value would be 1. Okay, so first would be this, then we would have this, yeah, so there's double bond here, so multiplied by 2 here, and here. So next is all possible isomers of C4H10O. So it would be, if you calculate dB would be 1. So no RTFMCP, no ring chain. Whether it has tautomers or not, we'll find it out, but definitely it is having functional groups. We can tweak between OH. We can have, it will have two optical active isomers. Okay, then we can have functional group isomer as this. Now we can have metamers like this. Okay, so now this is done. This is metamers not there, metamers are done. Then now chain, so we can actually bring the chain length down to 3 and then again attach OH here, or it is also possible to attach over here. Okay, so chain and position are also covered. Okay, so the last example for this lecture is draw all possible isomers of C4H6. If you calculate the dB value, I think the dB should come out to be 2. Okay, so this is the first one. Now we have this one, and this one. So this was for the rings have all been covered. Now is there any tautomer? I don't think there is any tautomer, ketonal forms or something like that. Is there any MF? No, FMCP. Functional groups, yes, we can change between double bond and a triple bond. So let me draw the first double bond. Just let have cumulene, alternate double bonds. Now I'll draw triple bond. So functional group, oh sorry, triple bond. So functional group, there is no metamer, there is only single chain. The position can be, I am also varying the position in cumulene, and uh, alternative double bonds are conjugated, uh, alternate double bonds only. Okay, and this. Okay, so with this we come to the end of this lecture and end of the isomerism as well. So in the next lecture we will be talking about DL configuration of compounds, how to make the DL configuration. Okay, so till then, good luck and goodbye.